Good evening, everyone. Welcome to the week 9 live interaction session for the course Polymer Concepts, Properties, Uses, and their Sustainability. So, as usual, let's just wait for a few minutes for others to join before we begin our session for today. Let's begin our session for today. Let me just share my screen. I hope my presentation is visible and I am audible. Okay, so let's start our session. So, good evening, everyone. Welcome to the week 9 live interaction session for the course Polymers Concept, Properties, Uses, and Sustainability. This course is offered by Professor Abhijit P. Deshpande from the Department of Chemical Engineering, IIT Madras, under the NPTEL program. Myself, Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati, Assam, is one of the TAs who is responsible for conducting the live interaction session every week. So we have so far come across 8 weeks of this course, and in the last week of this course we discussed about some of the concepts of polymer properties and their uses. So we discussed so I hope everybody is able to recollect what we have discussed in week 8. So just as a recap, so what we discussed in week 8 was typically based on the trait test for polymers, where we discussed about how to measure different, or what are the different types of trait tests that exist for the polymers to measure certain properties of them or to test their commercial feasibility. So these, as we time and again say, these are not going to test the properties of the material, but these are going to test about the, or these are the tests for the products fabricated from the polymer materials. So we discussed about different types of trait tests. So the most common trait test that we discussed was on the hardness. So apart from hardness, we have scratch, puncture resistance, as well as tear strength. So in case of hardness, we discussed about how to test the hardness of a particular polymer product, and we discussed about a technique so called as nano indentation, and how it is used to measure the hardness of a material. So similarly, after discussing about the trait test, we discussed more about the polymer blends, and we discussed how does this polymer blend affect the properties of the material, and how a blend is different from that of a copolymer. So here we typically took an example of ethylene propylene homopolymers, where we wanted to see how ethylene propylene homopolymer and ethylene propylene copolymer differ in their aspect of impact strength. So we observe that in case of a polymer blend out of these two homopolymers, the impact strength is going to remain the same. However, when a copolymer is prepared out of these two monomers of ethylene and propylene, what we are going to observe is an increased impact strength. So we discussed about that, and we also discussed about how polymer blends are formed in detail. So moving on further with that, we discussed about the polymer blends using conducting polymers. So where we try to add a conducting polymer to another polymer and form a blend, so that we can incorporate certain functionality to the polymer. So this is typically far more exploited in case of the electronics or wearable electronics application. So in that particular area of research, since conducting polymers are typically rigid and brittle, they cannot be stretched. However, in order to bring stretchability for this kind of material, polymer blends always remain a choice for always remain a choice to bring about conductivity as well as flexibility in these polymers. So what they typically do is they take a conducting polymer phase and a non-conducting polymer and form a blend out of these two, so that the resulting mixture exhibits certain flexibility, stretchability, or to be in a general sense exhibit certain level of mechanical properties, at the same time also have good amount of electrical conductivity imparted in their blend. So this is a particular place where polymer blends are often used. Of course, there are also other areas where polymer blends are common or provide more advantage to that particular field. Further, going on with that, we discussed about biomimetic polymers and how they are different from bio-inspired polymers. We discussed about few of the examples such as artificial nose, artificial skin, and we also discussed about the synovial fluids. After this, we discussed about a particular concept on polymers, which is nothing but the diffusion of polymers. So before discussing about diffusion of polymers, we discussed about the fundamentals or basics of diffusion, the Fick's law of diffusion, and how mass flux is proportional to the mass gradient or the concentration gradient, or to be in a more chemical engineering sense, it is basically the gradient of the chemical potential. So we discussed about how this diffusion or the diffusivity varies in case of gas, liquid and solid depending upon the type of arrangement of the atoms and molecules in the structure. Then we discussed about the diffusion of polymers, and we also discussed about the equations that relate the diffusion of small molecules in case of the polymer. So this diffusion typically is more important in case of when you go for water separation or membrane related or gas separation applications, where you need to understand how polymers can be used as a membrane or how the diffusion of these small molecules happens in these membranes. So in those particular applications, this diffusion properties of polymers are of great significance. So this is for the last week. So in today's live interaction session, the week 9, we are primarily concerned about polymer processing and their recycling techniques. So in today's live interaction session, our focus will be on two different topics, or you can say three: polymerization kinetics and reactors, and polymerization processing, or you can say polymer processing. So these are the three areas that we will concentrate for this week's live interaction session, and we will also solve some of the problems related to the concepts that we discuss in the next half an hour. So polymerization kinetics. So here we typically discussed about how the polymerization is going to be affected, or what are the different parameters, or you can say the variables that affect the polymerization process. So as all of us know, the polymerization route, or in order to form a polymer out of a monomer, that particular route of conversion is not going to be same. Different monomers undergo different type of polymerization technique. There are a lot of different types of ways to polymerize a particular monomer or for a polymerization reaction to happen, but the most commonly discussed three types of polymerization are nothing but the free radical polymerization, step growth polymerization, and then the last one is the living polymerization. So free radical polymerization, as we have seen in the earlier sessions as well as in the course lecture, that it typically uses a free radical for the polymerization reaction. So you have a monomer, and to that monomer you add a initiator, and that initiator reacts with the monomer to form a monomer free radical. This monomer free radical interacts with the other monomer, forming another radical. So this keeps on happening, and then the chain continues to increase in the length, and at one particular point the chain terminates to form a particular polymer, or to form a polymer of a certain length. So this is about the free radical polymerization. So in case of free radical polymerization, we have totally three different steps. First one is the initiation, second one is the propagation, and third one is the termination. So the rate of polymerization over here can be, since we are going to discuss about the kinetics, the very first thing that as we speak about a kinetic of a particular system, what we get, the very first thing that strikes our mind is the rate at which that particular reaction is going to happen, or the rate at which the process is going to occur. So here, since the process is going to be polymerization, we are more interested in seeing how fast or how slow the polymerization reaction happens, or to specifically say this, the rate at which the polymerization happens, or rate of polymerization. So here the rate of polymerization is nothing but it is equal to that of the rate of propagation. As we discussed before, since these free radicals are going to go and attack other monomers and then form another free radical, which then again looks for another monomer, attacks it, and then forms a free radical forms another free radical. So the propagation step is going to be the slowest step, which is going to be the rate or a rate determining step. So that is the reason in case of polymerization for free radical, the rate of polymerization is nothing but it is equal to that of the rate of propagation. So the rate of propagation is typically represented or is given as Rp, that is rate of propagation, is equal to Kp. Kp is nothing but is the rate constant of propagation. Cm, so Cm is nothing but the concentration of monomer, and Cm dash. So this is the concentration of the free radical that gets generated within the system. So based on this, we can write the rate of polymerization as Kp times Ki by Kt whole power 0.5 times Ci power zero point 0.5 times Cm. So this is the rate of polymerization. Here Ci is nothing but the concentration of the initiator, and the Ki and Kt are nothing but the rate constant of the initiation reaction and the rate constant of the termination reaction. So based on this rate of polymerization, we can calculate the value of number average molecular weight, which is nothing but it is typically represented as xn bar, which is equal to kp times cm by 2 root over ki kt ci. So how many of you here can actually derive this rate of polymerization what I have given for free radical? Because this step that I have given, or the equation that I have given, actually has a particular derivation. So my question is, how many of you are comfortable with the deriving this rate of polymerization reaction as well as the xn bar, or you can say the number average molecular weight? Anyone who will be willing to actually derive this? So this equation, since cm star is actually is going to be an intermediate in the reaction, and since we cannot calculate the concentration of cm star, which is going to actually vary with time, we are supposed to represent cm star as a function of ci with values that we know. So this is the basic of chemical engineering, chemical reaction engineering. So over there, certain steps or certain the rate determining step will have concentration terms of intermediate molecules or intermediates that gets formed during the reaction. Since it's not possible for us to determine the concentration of the intermediate, or that intermediate whatever that is formed in the reaction, its concentration is going to vary with time, we try to represent the rate determining step as a function of the parameters that we know. So that is the reason we represent cm star as uh, cm star with the parameters that we know, that is in terms of ki, kt and ci. So my question is, how many of you actually know how to derive this rate of polymerization reaction based on rate of initiation and rate of termination? Yes, anyone? So please have a look at the lectures. So over there you can actually find out the rate of initiation, rate of termination, those equations, and once you have those two with in hand, I think calculating rate of polymerization will not be a difficult task. So based on that, you can also calculate the number average molecular weight. So this is about the free radical polymerization. Similar to free radical polymerization, we have something called a step growth polymerization. So the main reason why it is named so is because the polymer chain grows as in the form of steps, like how it happens in case of condensation polymerization. So that is typically the reason why the rate of polymerization here, if you see, is described in terms of the concentration of the alcohol as well as that of the acidic group, such as what you can see here, KpCOH square or KpCOH square. So this is represented based on the assumption that the stoichiometry is going to be equal. That is the concentration of the monomers with the alcohol group and with the acidic group, their stoichiometry is going to be the same. Or you can also say that the functionality or in this case is going to be 1. After the step growth polymerization, what we are going to have is the living polymerization. So anyone have any guesses on why this particular polymerization is called as living polymerization? Or what is the unique thing about living polymerization compared to the first two, that is your free radical and step growth? Yes, anyone? So the major reason why it is called living polymerization is because the termination step in case of in this particular reaction is not going to be present. So this polymerization is going to happen till the monomers are present. So even if you have infinite amount of monomers, the polymerization process is going to continue until or unless all the monomers are consumed in the process. So infinite monomers, then the chances that the polymerization will happen or will continue to happen is infinite. So this living polymerization is typically ionic in nature, and the rate of polymerization here, since there are no initiators that are added, or it's just that the only the active active centers are going to be present. So here the rate of polymerization typically only depends upon the concentration of the monomer. So that is the reason why you can say that the rate of polymerization reaction depends only upon the concentration of monomers, so it is represented as kpcm. Similarly, the number average molecular weight is going to be represented as cm by ci. So here, since it's going to be only the monomers which is going to actually determine how long a reaction or at what rate a reaction is going to progress or polymerization is going to happen. So the rate of polymerization here is nothing but kpcm. So this is about the three types of polymerization kinetics. So these three polymerization is nothing but the fundamental mechanism that governs a particular polymerization process, or these are the three routes for the polymerization. But when you actually scale it up, or when you think from the industrial perspective, or to scale up this polymer process, there are different types of polymerization processes which are used for scaling up this scaling up the production of polymers. So the typical, so as you know, the examples could be solution polymerization, bulk polymerization, precipitation, suspension polymerization, emulsion polymerization, and gas phase polymerization. Each of these techniques have their own advantages. So if you see, in case of suspension or the emulsion polymerization, typically in those cases, if you see, in case of suspension, if you use a monomer and a solvent, say for something like example of water, the monomer is not going to, in majority of the cases, the monomer is not going to have an intermolecular mixing with the solvent. So they tend to remain as droplets suspended within the solvent or surrounded by the solvent medium. So in these cases, the droplets of the monomer acts as a center or an active center which is responsible for the polymerization reaction. Similarly, in case of the emulsion polymerization, what is the typical difference is that in emulsion polymerization, a surfactant is going to be added which creates the micelles. So these micelles are the ones which are going to be the center for the polymerization reaction, or you can say these micelles kind of act like reactors for the polymerization, just like how it happened in case of droplets for the suspension polymerization. In case of the gas phase polymerization, this is typically happens in an heterogeneous phase. So here, depending upon the heat that gets produced during the polymerization process, the reaction kinetics will vary for the gas phase polymerization. So depending upon the type of polymers that we want to produce, we actually choose which kind of industrial polymerization process we want to typically carry out. So in case of, let's say, polystyrene, we either go with bulk or suspension or emulsion polymerization. Similarly, in case of LDP, HDP, the industrial process varies. Likewise, in case of PMMA, ABS, each of these different polymers are usually produced through different industrial process. So that typically depends upon what type of polymer we are actually going to produce, or which we actually want to scale up. So this is about polymerization kinetics and the reactors. So once the polymer is made, it is usually required to be processed so that it can actually be used, or to make it ready for the human use. So that particular concept is called as the polymer processing. So in order to do this polymer processing, we typically go, before this polymer processing process, we use certain unit operations, or certain unit operations are performed based on the requirement of how the polymer is going to be processed, or how we want our polymer products to be. So the typical unit operations include mixing, and then so mixing is one. Any other type of unit operations related to polymer processing? Anyone? There are multiple type of unit operations that are possible. One is actually the mixing. Apart from that, there are also other types of mixing operations, like for example, anyone examples of unit operations. So once this unit operations are done, we go for the processing of the polymers. So there are different types of processing techniques, starting from extrusion, then injection molding, compression molding, film blowing, blow molding, coating, calendering. So you can have a look at these process, each and every process that we that I have told here is indeed a very big concept where we need to learn about what is the type of process, what are the kind of variables that affect the process, and what kind of plastics or polymers you can obtain through this process. So each and everything, if you go, so it will be if you try to search down for each of this process, you can get a detailed lecture or basically notes where you will be able to understand about how each of these techniques is different from one another, and what is the basic working principle behind these kind of polymer processing techniques. So however, in all these cases of polymer processing techniques, one thing is going to remain important, or which will affect the processing way. So that is nothing but it is the flow behavior of the polymers, or you can say, as we are familiar with the term now, the rheology of the polymers. So the rheology of the polymers is going to be of a subject of discussion here, because they are going to typically determine how these polymers can be processed, or what kind of different techniques can be used for processing a particular polymer. So when we talk about polymer flow or polymer rheology, so here we need to discuss about the basics of rheology before progressing towards polymer rheology. So when we talk about rheology, we actually means that we try to understand the behavioral pattern or the flow behavior of a particular fluid under stress. So based on this, there are two types of classification. So one is nothing but is the Newtonian fluid, and another one is the non-Newtonian fluid. So in case of the Newtonian fluid, they actually obey the Newton's law of viscosity, which is nothing but shear is directly proportional to the strain rate, with the viscosity as the proportionality constant, as many of you over here might know. However, in case of non-Newtonian fluid, this relationship does not remain valid anymore. Here, the shear stress is not going to be proportional to that of the strain rate. So polymers are an excellent example of the non-Newtonian fluid, or those fluids which does not obey the Newton's law of viscosity. So depending upon the type of or depending upon how the polymers or the fluid ex, uh, exhibit their flow behavior, this non-Newtonian fluid, or depending upon the type of how this polymer responds to the shear stress, the non-Newtonian fluid can be described or can be classified into three different types. One is the pseudoplastic, another one is the dilatant, and another one is your Bingham plastic. So any idea on what is pseudoplastic, dilatant fluid, and Bingham plastic? Anyone? How does a polymer behave to the stress? Based on this, we have three classifications. So one is going to be a pseudoplastic, another one is going to be a dilatant, and another one is going to be a Bingham plastic. So how do they vary with stress? Anyone? Okay, so we will have a question related to this. So let us see these three, or let us discuss more about these three terms when we are discussing that particular question. So apart from that, we also have to discuss something about so called as a melt flow index, which is nothing but it's a industry, more often an industrial parameter. So this typically determines, or it measures the amount of polymer melt that flows out of a die under a standard mass in a given time. So how much polymer actually flows out of a particular die under a standard mass and a given time of condition is called as the melt flow index. So these kind of parameters are typically important when we discuss about the polymer processing technique. So out of all the polymer processing techniques, we will be discussing or concentrating mainly on two, and you can say they are the most common. First one is going to be an extrusion, and second one is going to be nothing but is your injection molding. So extrusion as such, you when you say the term, you actually try to mean something you are extruding or something you are drawing out of something. So that is what is actually the extrusion process. So all these polymer process are something which you can actually imagine, or which you can actually easily visualize. So in case of polymer extrusion, so if you see the lecture, the last lecture for week 9, you can actually see single screw extruder, where which is, I think with that, but that figure is a very clear one, where you have different types of zones and different paths marked, and also a clear explanation is given for that particular process. So here let us summarize that into very short. So in case of extrusion process, what actually happens is the polymer that you are trying to process here is going to be present in the form of a polymer pellets. So, or in case of the polymer solids, you can say like chunks. So these polymer pellets or chunks are going to be feeded or fed into the extruder or the screw extruder using a hopper. So you have a hopper, and to that hopper these polymer pellets are added, which then gets transported to the screw extruder. Once this polymer enters that extruder, due to the motion of the screw or the rotation motion of the screw, these polymer pellets are going to be moved forward towards the end portion, that is nothing but where your die is going to be present. So as this polymer pellets actually move, they are also going to be heated up by two means. One is basically an external source of heat supply, and another one is going to be their friction, as well as that of the viscous heat that going to get generated as they move forward through this rotational motion of the screw. So because of that, what happens is the polymer pellets are, because of the heat that gets generated, the polymer pellets are going to form a polymer melt. So as they reach towards the end of the screw or move closer to the die, majority of the polymer pellets are going to be formed as a polymer melt, or you can say that they are going to be present in the form of a molten polymer. This molten polymer, what happens is, when this molten polymer reaches the end of the die, they are forced through the die, and when they are forced, and when this molten polymer is forced through the die, they are able to achieve their desired shape. Once the desired shape is achieved, this particular polymer products are cooled and solidified. So this is typically the entire process. You have polymer pellets, you feed the pellets into the extruder. Because of the motion of the screw, they move forward, and during this motion the extruder is heated up. Because of this external heating as well as that of the viscous dissipation and the external and the friction that the pellet encounters, the polymer pellet is is heated and it forms a molten polymer. This molten polymer reaches the end of the screw and is forced through the die to achieve the desired shape. Once it achieves the desired shape, it is cooled and solidified. Now, so this is about only the process. So in order to in order to apart from polymers, this polymer can also be mixed with certain other additives. For example, some sort of a stabilizer or some other additives, or you can say even this coloring agent. So your polymer plastic that usually comes is has multiple colors. It usually comes in the form of red color, purple color, yellow color, green color, all different types of colors that you can actually visualize. So in order to add color to this polymer, coloring agents are also used. So they are also fed with the polymer pellets before itself. So they are mixed with this polymer pellets and then they are fed. So this is a process of extrusion. So again, as this process happens, there are also certain factors, or you can say parameters, that affects this extrusion process. So here we will just quickly list a few of those variables, or you can say the process parameters that affects this extrusion process. One is going to be a screw rotation speed. So the faster the screw moves or rotates, the pace at which the polymer pellet is going to be heated up and then is going to be forced through the die is going to increase. Then next one is the viscous heat dissipated. Third one is going to be your fiber breakage. Because of the shearing action between the molten polymer and the solid pellet, there are chances that the fibers will tend to break. After this, you have the die opening. Apart from this, there are also the screw dimensions which is going to affect the process. So the first one is your nothing but it's going to be a diameter as well as the compression ratio. Then you have the length to the diameter ratio. So the length of the screw and the diameter of the screw also affects how the process takes place. Then the third one is going to be your channel depth, which is going to affect the strain rate. So this is about the extrusion process. Apart from the extrusion process, we also have a injection molding. So before this going on for the discussion of injection molding, if you have any doubts related to this extrusion process, you are welcome to ask now before we progress for any further. Yes, anyone? Any questions related to the extrusion process or any other thing that we have discussed so far? Okay, so let's move on towards injection molding. So, like how you see, this extrusion is a continuous process, this injection molding is also, it is more of a cyclic process to produce parts by injecting the polymer melt into the mold. So here you will have a mold, and to that particular mold, as the name suggests, the polymer melt or the molten polymer is going to be injected, and based on the shape of the mold, the polymer melt will, or the polymers will take that particular shape, and then the products will be obtained based on that. So here what happens is, first actually the mold for the injection are usually in the form of two halves. So you have two half of the molds, and these molds are basically connected together, and the polymer or the molten polymer is then injected into the mold, and it fills the cavity that forms after connecting this half of the mold, or halves of these mold. So the material is the material is feeded into this cavity under pressure, so that it ensures complete filling of the cavity and prevents any form of leakage or shrinkage. Once this cavity is filled with the polymer, the sample is cooled along with the mold and is allowed to solidify. Once it is solidified, the mold is opened, and then the part is ejected out. After this, the process again continues. So this particular process is injection molding. It's a very simple process. The major major concept is that the mold, that the polymer, molten polymer, is injected into the cavity of the mold, and then that, once the entire cavity is filled, the mold is going to be cooled, the polymer melt, as well as the mold is going to be cooled and solidified. Once solidified, the mold is open, and then the plastic part that is formed is ejected out. Same way as we have seen, each of these process what we are going to discuss typically have certain key variables that affect the process, or you can say there are certain process parameters which is going to affect the process, no matter whether it is going to be extrusion, injection molding, compression molding, or film blowing. Each and every process has certain factors that affect their process, or that tend to determine the way the process actually works. So here the operating conditions in case of the injection molding, so there are totally two different variables, one is the temperature and the other one is the pressure. So in case of high temperature, what actually happens is the thermal energy that the polymer melt will carry with them is going to be high. So because of this, they are going to flow more easily compared to a one with the lower temperature. So because of the easy flow, the viscosity is going to be less, so the pressure that is going to require is going to be low. However, at very high temperatures, there are also chances that there will be thermal degradation. Again, as we said now, at high temperature it's going to be easier to fill the cavity, but similarly, if the temperature is going to be low, or it's going to be not that sufficiently high, then what is going to happen is the ability to flow is going to be restricted, and because of this, a high viscosity is exhibited by these polymer melt, so it becomes far more difficult to fill the cavity compared to the polymer melt which is at a elevated temperature compared to the one that we have at low temperature. Similarly, there is also pressure. So if you have a very high pressure, then what actually can happen is that the polymer melt can overflow through the mold, and in case of low pressure, there is a possibility that there can be a significant shrinkage that will be obtained in the polymer product. So this is how what is the thing that we have to take is, all these process parameters need to be optimized. They cannot remain very high or they cannot remain very low. So these process parameters need to be optimized so that we can achieve our desired product. So this is about injection molding. So our discussion part actually ends here. So if you have any question, you are welcome to ask me before we progress for the problem solving session. So we will start our problem solving session at 6:10. So till then, if you have any questions, you are welcome to ask me. Please let me know if you have any questions. Anyone with any questions? So in case if you have no questions, then let's move forward for our problem solving session. So the very first question for today's live interaction session is going to be question number 1. Melt flow index of a polymer depends upon its molecular weight and melt viscosity. Select the correct relation or relations from the following options. So you have 4 where it is typically whether the melt flow index is going to be directly proportional to viscosity or is going to be inversely proportional to viscosity. Similarly for that of the molecular weight. So here what will be the correct relation? Anyone? So as we said before, null flow index is nothing but it's going to be an industrial measure to check for the polymer's flowability. So it's basically a measure about the amount of polymer that flows out of the die under a standard conditions in a given time. So based on that, we need to see whether this melt flow index is going to be how it is going to vary with respect to its molecular weight and viscosity. Again, here there can be more than one choice. Anyone who knows? I think this should not be hard. So I think it would be easy to describe how this melt flow index is going to vary with the melt viscosity. So anyone at least on that, whether is it going to be directly proportional or is it going to be inversely proportional? So melt flow index is something which determines the amount of polymer melt that can flow. So that means that greater the melt flow index, greater will be the amount of flow of the polymer that flows out of the die. So based on this, we need to discuss how it is going to affect with the molecular weight and melt viscosity. So it is going to be inversely proportional to melt viscosity, because as I said, higher the melt flow index, which means more amount of polymer is going to flow. So that actually means that the polymer is going to flow more easily, because once the polymer flows easily, more amount of polymer, it is eventually it can be correlated that more amount of polymer will be flowing because of the easy ability at which the polymer flows. So ease of flow of polymer means viscosity of that polymer melt should be low. So higher the melt flow index, the viscosity should be low, so which means it is going to be inversely proportional. So similarly, what about its relation with the molecular weight? How does the molecular weight going to affect your melt flow index? Again, same relation, keeping in mind the same relation that higher MFI means higher amount of polymer is going to flow out of the die. So how does the molecular weight play a role in this? So there also it's going to be inversely proportional. Am I right or wrong? It's going to be inversely proportional because higher the weight of the polymer, it will basically make the polymer difficult to move. So higher the molecular weight, less will be it will be difficult for the polymer to move out or basically flow. So lower is the melt flow index. So which means it's going to be inversely proportional. Is this fine? So this is the answer. So both melt viscosity as well as the molecular weight is going to be inversely proportional to that of your melt flow index. So coming to the next question, a high molecular weight polymer is going to pass through different zones from the hopper to the die in an extruder. Among the options given, identify the correct match between their zones and their key functions. So you have totally three different types of zones. One is your metering zone, compression zone, feeding zone and working zone, and you have certain key functions that are listed in the column B. So based on that, we are supposed to match which zone have what particular functions or exhibit what type of functions. Anyone? First, let's start with the feed zone or feeding zone. So that should be matched with what? So R, let's first match R. So R should be for 2. So the feeding zone is obviously the zone which actually receives the charge or whatever the feed that you're going to input. So R is 2. Now what about the rest? P, Q and S. What about metering zone, compression zone and working zone? Compression zone. So Q can be 3, melts the charge on the feed through heat conducted by the heating element. Is it fine or can it be also something else? So it is 3, melts the charge of feed through heat conducted by the heating element. Now what about metering zone and working zone? Can this working zone be one? High shear forces for effective mixing. Is it okay? Any response or any idea or any thoughts on this? And P is actually 4. So the metering zone is basically the zone where the charge or your feed is going to acquire a constant flow rate by the screw. I think this might be a bit confusing, so it's better to actually look at this question with the help of a single screw extruder picture. So what we can do is we can actually take this question once again in the next class, so that with the picture of a single screw extruder, so that we can actually clearly know what are the different types of zone, where they are located, and what are the functions of each zone. Is it okay? So let's have this question for the next class as well. So moving on, the next question should be a bit more simple. So you have a plot which shows your apparent viscosity versus the shear rate for Newtonian, dilatant, and pseudoplastics. Based on this observation, we are supposed to say what type of fluid behavior it is. Show the correct combination. So this is something that we discussed before. So I asked a question about how does a particular polymer, in case of a non-Newtonian fluid, how their viscosity varies with shear rate. So that is exactly the same question that we have right now. So this is exactly based on the definition of pseudoplastic and dilatant. I mean pseudoplastic fluid and dilatant fluid. Just based on the definition. So which one will be matched with P, Q and R among 1, 2 and 3? So at least which one will be the Newtonian fluid among P, Q and R? Yes, anyone? So, can we match? So, as per the definition, Newtonian fluid is nothing but it is going to Newtonian fluid. For Newtonian fluid, the viscosity is going to remain independent of the shear rate. So, there will not be any kind of changes in the viscosity of the fluid with respect to that of the shear rate. So, can you say P as Newtonian fluid? I mean, this is as per the definition. So, is this fine? Now, coming to Q and R. So, you have two dilatant and pseudoplastic fluids. So, which one is going to be pseudoplastic and dilatant among Q and R? So, as per the definition, so I'll be posting this definition along with the slide when I'm uploading them in the Google Sheet. So, for the time being, let me just explain it verbally, but you will be able to get the written definitions along with the slides when they are made available. So pseudoplastic is the one in which the viscosity is actually going to decrease with the shear rate, and in case of the dilatant fluid the viscosity or the apparent viscosity is going to increase with the shear rate. So as per definition, pseudoplastic means viscosity decreases with shear rate. So here among R and Q, which one has a decreasing trend with the shear rate? It is Q. So and R is going to be 1. So is this fine? So R means apparent viscosity increases with the shear rate. So that is something that is typical for a dilatant fluid. So this is with respect to the multi-choice questions. I hope there are no doubts. In case if you have, you are welcome to ask me now. For those of you who do not have any doubts, let me put forward the next question, which is again it's a very simple question. So in an anionic polymerization experiment, number average degree of polymerization is found to be 600, and the concentration of the styrene monomer is going to be given as 0.15 mole per liter. Calculate the concentration of the ionic initiator. So as we know, in anionic polymerization, so in living polymerization, since it's ionic in nature, you have two types. One is anionic and cationic. In anionic polymerization, it is written that, so in anionic polymerization, apart from the monomer, you also have an ionic initiator. So based on the concentration of the monomer and the ionic initiator, the number average degree of the polymerization is going to vary. So here we are given with that number average degree of polymerization and the concentration of the styrene monomer, but they are asking us to calculate the concentration of the initiator. So how to solve this question? It's a simple question. Anyone? It's just a single line. So the answer is, it's a very very simple question. You just need to know how to calculate the number average degree of polymerization for a living polymerization, and then once you know that, the problem is solved. It's just a basic arithmetic after that. So let me just give you the formula. So in here, so this one is going to be the formula. I think now the question is solved. So let me write it. So xn, I mean the number average degree of polymerization is given as 600. The 600 should be equal to Cm. Cm is nothing but it's the concentration of the monomer, which is styrene in this case, and that is given as 0.15. And concentration of the initiator is something that we are asked for. So Ci is nothing but 0.15 by 600 mole per liter. So what is 0.15 by 600? 0.25 times 10 to the power minus 3 mole per liter. So this is the concentration of the ionic initiator. So as you can observe here, that the concentration of the ionic initiator is going to be very much less compared to that of the styrene monomer that we are taking. So again, here you can actually get questions in multiple other forms, like again, so the equation is going to remain the same, but you can be asked to calculate the number average degree of polymerization by providing the value of concentration of the monomer as well as ionic initiator, or you can be asked to calculate the concentration of ionic initiator as we did here right now, or you can also be asked to calculate the concentration of the monomer by providing both the values of the number average degree of polymerization and the concentration of the initiator. So again, this is a simple arithmetic problem. So only thing that we are supposed to logically, what is involved is how to calculate the number average degree of polymerization in case of the anionic polymerization reaction. So I hope there won't be any doubts in this case. So if you have any, you're welcome to ask me. Meanwhile, let's proceed for the next question. Next question is also something very similar. However, previously we saw for anionic polymerization. Here we are going to see for free radical polymerization. A free radical so let me read out the question. A free radical polymerization process yields a polymer with the number average degree of polymerization as 100. Monomer concentration is going to be doubled and the initiation concentration is increased by 4 times. Assuming all the rate coefficients and other parameters remains unchanged, calculate the new value of xn dash and comment about the rate of polymerization also. So here you are asked to calculate the new value of xn and how the polymerization rate is also going to change when the monomer concentration is going to be double and initiation concentration is going to be quadrupled. So what will be the value of xn dash or new xn? So how do you calculate this value? So for this we are supposed to know how to or what are the factors does this number average degree or actually depends upon in case of the free radical polymerization. So let me just give you the question, I mean equation. So based on that, so based on this, I think now you might be able to comment. Again, other all the other rate coefficients and the parameters are going to remain unchanged. They are going to remain the same. So So your number average degree of polymerization is 100. So for this, the Kp Cm by now the monomer concentration is getting doubled. So let us keep that as Cm dash, which is nothing but 2 times of Cm, and your initiator concentration is going to be increased by 4 times. So Ci dash is nothing but it's going to be equal to 4 times of Ci. So now substitute this. So then what you will get is Xn dash is nothing but, so all the other parameters are going to remain changed. So Kp C, so let's copy this equation. Kp Cm dash to Ki and Kt is also going to remain the same. It's only the Ci which is going to change. Ci dash. So now based on this, so express the Cm dash and Ci dash in terms of Cm and Ci. So then what we will get is equal to, so this Cm dash is going to become 2 times of Cm, and your Ci dash is going to become 4 times of Ci. So is this fine? So can we write it this way as Xn dash, or now, or the new average, a new number average degree of polymerization is equal to 2 by root 4. So root 4 is going to be again 2. Let me write this as root 4 first for clarity. So that means root 4 is nothing but it's equal to 2. So 2 by 2, which is 1. So x and dash is also going to be equal to kpcm by 2 root over kikt times ci. But again, as we saw previously, this is nothing but it's equal to xn itself. Is this not correct? Just a second. Sorry, there was a network issue. So this Kn dash is equal to Kpcm by 2 root over Kiktci, because this turned out to be 1. So this is something same as that of the previous Kn. So the value of Kn dash is equal to K, sorry, the value of Xn dash, that is your new number average degree of polymerization, and then the older number average degree of polymerization reaction is going to be the same, and that equals to 100. So this is about the number average degree of polymerization. Now we are supposed to comment also about the rate of polymerization. So the rate of polymerization is given by this equation. No. So based on this, we are supposed to let me make it like two columns. Let me bold this. So now we have to comment also about the rate of polymerization. So substituting what we have previously to here, how much we get. So let's do that substitution as well. So please do it parallelly along with me so that it will be useful. So rate of polymerization is going to be, so all the other parameters are going to remain the same, but your concentration Ci dash is going to be nothing but 4 times Ci. So this is, let us keep this as the older one, and same thing, let us keep this as a new one. After that, monomer is double and initiator concentration is increased to 4 times. So then this will be nothing but the entire dash. So this is the new one. So now we substitute these conditions and then check what we are going to get. So new rate of polymerization is nothing but it's equal to, as we said previously, these parameters are not going to change, so I am going to substitute them as it is. And in the, so substituting the Ci dash whole power 0.5 in terms of Ci, so you will have 4 Ci whole power 0.5 times Cm dash, which is nothing but it is 2 Cm. So now what you can write as, so 4 Ci whole power 0.5 is nothing but 2 Ci power 0.5 times 2 Cm. So this rate of polymerization is going to be, so 2 times 2, that is 4. So let's bring that 4 outside. So this is nothing but, so this term Kp, Ki, Kt power 0.5, Ci power 0.5 Cm is nothing but it is the same as the rate of polymerization, the previous one before these changes were made. So that means this rate of polymerization is going to be 4 times that of the, so the new rate of polymerization is equal to 4 times that of the older rate of polymerization. Let me just, so I hope, so if you have any doubts, you are welcome to ask me now based on what we have discussed related, what we have discussed so far. Any questions from anyone? So we have two more questions, but since we are running short of time, so we will not be discussing these two questions today. Let us take it for the, again, the question number 5 is going to be very similar to what we have solved in the last last week also. It's again about the relaxation time and then the um, constant stress as well as constant strain. So that is going to be as simple. So the other question we need to discuss it. So if you have any doubts, you are welcome to ask me now, or otherwise I think we can conclude our session for today. Is anyone with any doubts, any questions, anything that you want to let me know before we conclude our session? So let me just stop sharing my screen. So if you have any questions, then you are welcome to ask me right now, or I think we can conclude our session. So thank you all for joining today's live interaction session. Our next live interaction session will be on 28th September 2025. So I thank everyone for joining today's live interaction session. I hope it was useful. I thank Professor Abhijit Deshpande sir as well as the NPTEL team for providing me this opportunity to interact with you all on this afternoon. So let's meet for our next live interaction session. Till then, thank you and have a wonderful weekend. Bye.